So to get started, Matt, could you just tell us a little bit about what data science is? So there's some confusion from folks sometimes. Is that we talk about big data, we talk about machine learning. What does a data scientist do, and what is data science?
Yeah, sure. Thanks so much, Tom. So I want to share two numbers to set the stage for responding to that question. The first number, the University of Maryland CISM cyber attacks database reported a fourfold increase in the number of significant cyber events from 2014 to 2022. During that time, the number of significant cyber events reported has increased from about 500 to 2,000, so a fourfold increase. That number illustrates the significance of cyber threats. Now, keep in mind that number only accounts for the share of successful cyber attacks and the reported cyber attacks. So, in fact, there's far more attempts and unreported successful cyber events that have occurred. The second number, one of the ways to detect and track cyber threats is through Netflow monitoring. But a large organization may receive and generate close to 1 billion Netflow packets per day. And so that number illustrates the infeasibility of manually tracking data in order to detect cyber threats. And so together, I think that pair of numbers illustrates the need to use analytic approaches, including data science approaches, as part of a cybersecurity strategy. So to return to your question, what is data science? Modern organizations are inundated with data. There's a proliferation of devices in order to automatically collect data. So to return to the example of Netflow, an organization can put sensors on its network in order to capture packets. But these raw data by themselves aren't terribly useful. They just provide more or less a complete record of everything that happened. Data are distinct from actionable information. And so data science is the study of data to extract meaningful information from it. It's a multidisciplinary field that draws on mathematics, statistics, artificial intelligence, and computer science, to name just a few subdomains. And data science sets out to answer questions like what happened, why did it happen, and most critically, what actions should an organization take next? So a little bit about semantics. During this discussion, we're going to talk about machine learning. Machine learning is a component of data science. It's a class of methods that allows computers to learn how to perform tasks. This is useful when we don't have instructions that we can provide to a computer in order to teach it how to perform a task. No doubt, machine learning is a large part of data science, but the last point that I want to emphasize is that it is only one component of data science. There are other components of data science, such as generating descriptive statistics to describe what has happened, performing inferential statistics to understand the relationships between events and potentially to predict what will happen in the future, and then lastly, creating visualizations as a way to convey information to people.
Great, thanks, Matt. That's a great overview. So data science, to recap, we're looking at statistics, machine learning, visualization, all those tools the data scientists would have in their tool bag. And so with that in mind, there's a lot of issues that we're fighting in cybersecurity. Some are appropriate for data science, some maybe aren't. So Jeff, let me ask you, just in general, how do you frame a data science problem? What makes for a good data science problem so I know when I want to use data science?
Sure, Tom, and that's a great question. So data science is a sparse, overarching domain, and data science can be used to solve a wide array of problems, both in and outside of the cybersecurity domain. There's a number of things that go into making a good data science problem, and I won't come up with an exhaustive list, but a couple in mind are, one, a lot of these algorithms we work with are what is known as non-deterministic. So if I supply the same input data to these models and run that model several times, I'm going to get different results each time. And in doing this, we recognize that these solutions to these problems are only approximate. They're not exact solutions, but they're more cost efficient. Maybe we spend less money as an organization. Maybe we need less people, things of that nature. Another thing that makes a good data science problem is data availability. It's very difficult to come across both relevant and quality data. So first you have to ask yourself, is this data that I have, is it useful for the problem I'm trying to solve? Then you want to look at the quality of that data. Am I missing values in my data? Do I need to spend a good bit of time to clean up the data to be in such a way that I can use it? And lastly, I think what makes a good data science problem is for it to be applicable to society and practical in society, right? So it's fun to, come up with data science problems where they're more for sharpening our data science tools, just getting a feel for how an algorithm works. But a really good data science problem is one that, organizations, businesses, people in society genuinely care about.
Very good, thank you. So in the intro, I mentioned our data science for cybersecurity certificate program. In that program, we have courses that look at Netflow data and malware data and digital forensics data, as I mentioned. But one data science problem in cybersecurity that kind of pulls all those domains together is detecting and defending against APTs, advanced persistent threats. So folks in cybersecurity have been working to detect and defend against APTs for a long time. More recently, there's been some research in using machine learning for APTs and some different data science techniques. So I know that's something you're knowledgeable about, Matt. Can you tell us a little bit how we can use machine learning and data science to address APTs?
Yeah, sure. So just to provide a little bit of background, the name for this type of threat, advanced persistent threat, really describes its key characteristics. These threats are advanced in that they are supported by well-resourced adversaries. They can discover new exploits and leverage existing exploits in new and unseen ways. These threats are persistent, so they're not a one-time attack, but rather they're a wave of attacks against an organization. And then lastly, they're a threat, and a threat typically with the goals of evading detection and exfiltrating data from an organization. And so these three characteristics of an APT, advanced, persistent, and threatening, make it difficult to determine a set of rules in advance that a computer can use to determine that a particular program is malicious versus benign, that an IP address is threatening, that a pattern of Netflow data reflects that an APT is underway. And so because it's difficult to hard code a set of features to detect APTs, machine learning provides a natural set of tools to help close the gap. And in particular, there's two ways that you could go about using ML to detect APTs. The first are a set of methods that fall under the umbrella of supervised learning. So in this case, we have a set of historic data. For example, that data could be programs. And those data are labeled, so we can label the programs to say whether they were malignant or benign. With those data in hand, it's possible to train an ML algorithm to determine whether new programs are malicious or benign. So the strengths of this approach is that it is very effective at detecting threats that resemble, though may not be identical to, past threats that we've encountered. But some of the drawbacks, it requires historic data that are labeled, and as the nature of the threats evolve, then the detector will become less and less efficient. The other broad umbrella of approaches falls under the category of unsupervised learning. So with unsupervised learning, we may have historic data, for example, about the performance of a network. But those data are not labeled to say whether or not an APT is underway. So when using unsupervised learning, we may be seeking to reduce the dimensionality of the space. So to take this complex space and distill it down into a set of features that are easier to analyze. Or alternatively, we may be looking to characterize the normal operations of a network in order to detect unusual or anomalous events. So the strength of unsupervised learning approaches here is that it doesn't depend on having labeled data, but the drawback here is that not all advanced persistent threats will produce anomalies, and not all anomalies indicate that an APT is underway.
Very good. And so a follow-up question, you've been looking at this space. what would you say the current state is of using ML for APT? So is this something that someone can just download a pre-trained model and a tool and they're good to go? Or are they going to have to consult with a data scientist and write some, context-specific code? Or what's sort of the state of the field as you see it right now?
Yeah, right. So the use of ML for detecting APTs, there's at least two things that make this viable. The first is that there are data sets available for developing new ML algorithms and for testing those algorithms. So the availability of data for developing training and testing algorithms is an enabler. The other thing that makes this space promising is that many of the approaches that are being used for APTs are well-established approaches that have been applied to other supervised learning problems. So logistic regression, random forests, gradient boosting, neural networks. So all of those algorithms, which were developed without APTs in mind, are generalizable to this problem space. Having said that, there are nuances to applying these methods to new APT problems, and there are nuances to applying these within a given organization. So some amount of fluency in data science is needed in order to take those methods which exist and apply them in new contexts.
Okay, great, thank you. And so, one of the non-machine learning strategies that folks use to combat APTs is zero trust in networks. And one of the tenets of zero trust is, never trust, always verify. And that's great in theory, and sometimes in practice, that's not always something that can be done. And so I know, Jeff, you've been working with developing trust models for different scenarios like mobile networks, where maybe a device has been authenticated at some point in time, and you're not able to re-authenticate it. And so you want to model your trust, so trust decays over time. When should I stop trusting something that I've trusted in the past? So can you tell me a little bit more about the way we use data science in that work?
Yeah, absolutely, Tom. So first thing is to note that, network architectures today are becoming increasingly complex. We're at the stage where we're at, 5G and beyond. And it's ever important to have secure networks as well as devices that are trustworthy. So, so one way you can model device trust is with a couple different data science methods. But first, you want to get information about the networks that your devices are connecting to, and any information about communication between a device and other devices within that network, and individual information about that device itself. You can take all of that and use it as input data for a model, and that model can spit out a trust score for you. And essentially, a trust score is a quantitative assessment of how likely we are to trust device X. Right. And a couple things to note about a trust score is it's dynamic. It changes with time. As networks change and information about them changes, so too does the trust score. And you had brought up, trust decay as an example. So, we have a lot of assumptions. One of them is that as time goes on, gradually a device's trust score will decrease. And at some point, that device will need to reestablish trust with the network before it's allowed to connect. Now, the time frame for that is dependent on a lot of different factors. It's dependent on a lot of different factors. So there's no distinct, every week maybe is good enough, every month is good enough. So it's dependent on a lot of different factors. But it's also important to note that this is a probabilistic assessment. So these trust scores, a high trust score is indicative of a trustworthy device. A low trust score is indicative of a not trustworthy device. But they're not guarantees, right? Sometimes an untrustworthy device can slip through the cracks, right? And another way that this is probabilistic is our overall goal is to have a maximal amount of false positives that we allow do this. So in our situation, a false positive would be, we trusted a device, we thought it was trustworthy, but it actually wasn't trustworthy. And this can, seriously damage an organization.
Very good. And so, follow-up question there. So we're talking specifically about trust for devices and networks and the types of research you're doing. But really in all cybersecurity assessments, we're making a a probabilistic trust assessment when we certify a system to be deployed or something like that, that the risks to the system are low enough that we can accept them. So just in general, in any type of system I might be certifying like that, how would I go about, developing a trust score, identifying what components go into the score, and maybe testing out, exercising my trust score to make sure it has some validity? Any thoughts on that?
Yeah, sure. So a couple things that come to mind are, first off, you would want to know about, the architecture of the network itself, the things that make up the network. You would also want to know about any communication between devices. So something like maybe device A sent device B 10 emails in a 5-second period. You would think that there's something a little bit sketchy about that, right? You can also do something in the natural language processing world. It's a tool called sentiment analysis. And so what it does is it takes the content of, whether it be text messages or emails or whatever, and it produces a positive or a negative sentiment score, which, indicates the content of the messages themselves. And more often than not, a positive sentiment score will indicate a benign email. But it's not always the case. You can think of something like, congratulations, you won the lottery, now you're a billionaire, which is, clearly spam. But a sentiment score would indicate that might be, benign. But it's multifaceted. There's a lot of factors that go into it. And so I would say the main things are, information about the network itself, maybe the packet length of, device interaction, but also, content of messages being sent between devices.
Great, thank you. So on Go Back, we have a great question here from Timo in the audience. Probably for Matt, but either you can chime in. What type of unsupervised learning methods can be used for APT besides clustering?
Okay, yeah, I'll offer a response. Clustering certainly is one of the first methods that comes to mind. And in this case, we could identify a set of features and then, apply a clustering algorithm to take a number of records and try to partition them into separate clusters. But there are other approaches that one can use as well. One example that comes to mind is dimensionality reduction techniques. So it may be the case that if we're looking at a network or some other source of data, the input may have a very high dimensionality. That's to say there may be dozens or hundreds of different features that we can use to describe a particular record. And so dimensionality reduction techniques are one way to take that large set of features and distill them down into the top 3 to 5 to 7 aggregate features that can be used to describe each record. There are conventional approaches that one can use for that, like principal component analysis. Another thing that I've seen in the literature is using, for example, neural networks like autoencoders and decoders. So if you pass your records into the encoder, it distills it down into a latent space that has lower dimensionality than the input space. And that latent space may be a way that more easily allows you to detect anomalous events.
Great, thanks, Matt. Any thoughts on that, Jeff?
No, I thought that was pretty concise and a good foreshadow to later talking about some deepfake stuff.
Yeah, that was a good question because for those in our audience, who are just getting into data science or new to the field, kind of the classical questions that machine learning addresses is classification and clustering. So if I have a piece of malware, I may want to classify it that is malware, or it's benign, it's not malware. Clustering, I may want to say this malware is like other pieces of malware and put it in a family. So those are some basic functions of machine learning, classification and clustering. But as we get into it, there's a lot of other techniques in our tool bag. Some of that is what we teach in the program I mentioned, and Matt just elaborated on some of them.
Yeah, even to go back to the the network architectures that I was talking about, we were working with trust scores specifically, but you could also make it a classification problem. Maybe if a device has a trust score above 0.5, we're going to call that trustworthy, and below that untrustworthy. So you can kind of frame classification problems to be quasi-regression problems as well if you do it correctly.
Yeah, great point, Jeff. I like that because sometimes in data science, it's how we frame the problem. So there are things that at first blush might not be classification or clustering problems, but there's a way to frame it and shape it so that you can make those kind of analyses.
Right.
Very good. Another question from the audience, from Christian. How can we improve the recall and precision due to the context and data are different from each organization? So I think there's a broader question there about applicability across domains or organizations.
Yeah, right. And this is kind of something that I've seen a fair amount lately. So when training a machine learning model, the typical approach is to partition your data and keep one portion as the training data and to keep another portion as the test data. The idea being that you want to fairly test your model by providing it examples that it didn't include during training. So this is an effective technique to avoid overfitting models. But the question does come up, what if I take my model, which I've trained on one data set, and now I apply it to an altogether different data set? To give some other examples, this would be like training a medical classifier in one hospital and then using it in a different hospital, or training a model to predict some societal issue in one community and then applying it to another. That is the harder test of the model, to take it from the sample or population that it's been trained on and to try to generalize it to an altogether different population or sample. This is also the case with detecting APTs and cyber threats. A given organization can train a model, and it may be highly effective in that organization, but it may not generalize well to another organization. The two kind of pieces of advice that I have there. The first is that to not take as truth the performance of a model in one context. It needs to be evaluated in new contexts as well. The second is that even if the model doesn't generalize well out of the box, it is possible to take a pre-trained model and then, and this is called transfer learning, take a pre-trained model and then continue to train it with data from the new organization. And so in this way, you can effectively bootstrap the model's performance and achieve a high level of performance in a new context without having to entirely retrain the model.
Okay, great. Getting some good questions from the
Can
audience.
I just chime?
Yeah, absolutely.
So this person had mentioned recall and precision specifically, and it's all just, Matt had a great explanation. I just wanted to mention the idea of having well-balanced data sets. So you can create, say, a classifier, and maybe it predicts, spam or benign emails. But if you have a ton of spam emails only, the classifier is going to get very, very good at classifying spam as spam, but probably have a harder time classifying benign emails as benign.
Excellent, thank you. So I was mentioning we're getting some good questions from the audience, so I'm going to keep going with Q&A, and then we'll get back into some other topics. Okay. So this question probably be for you, Jeff, but I'm going to give a short answer, so give you time to think about it. What type of machine learning algorithm would you use to train a trust score model? So I just wanted to mention that some of the trust scores we've developed, the trust score itself is more of a deterministic math formula. And then we use machine learning to exercise the trust score and develop different scenarios. And so this goes to the point of data science isn't just machine learning. Sometimes we're just using statistical methods. Right. But I could also envision ways where you would use machine learning to train what constitutes trust or not trust to develop that trust score. So any thoughts on that?
Yeah, sure. So I mean, it's a really good question. Before you can't really go into the trust modeling with an assumption of the specific model you'll use, but you'll know what class of models you'll use. So for example, we were, working in the classification space. So that already narrows it down to, maybe I want to use a random forest classifier, maybe a decision tree classifier, maybe logistic regression, something like that. And I think it's good to try out several different models. It's not like logistic regression is the end all be all answer. You could even do some sort of ensembling method where you train a logistic regression classifier and a random forest classifier and sort of ensemble the model performance and stuff with that. But also with a classification algorithm, and how I mentioned classification problems can sort of be framed as quasi-regression problems is that a classifier will say you have a binary classification problem. We either have class 1 or class 2. When your model predicts where the data points fall into, it will give you back a probability of that being the case. So some data points will be that much more likely to fall into a certain class. Some will be close to the decision boundary, and things like that. But overall, I would say, try a couple models out. I don't think there's one end-all be-all model that, can be used to solve the problem.
Great, thank you. So we've been talking in this last little segment a lot about trust, and so there's trust and trust scores. There's also trust, and can you trust what you see and hear in video and audio? So that's another area we've been working is deepfakes. And so deepfakes are when folks typically using machine learning algorithms of some sort manipulate audio or video to create fake media. And so we've been working in the detection of deepfakes. And so I want to talk about that a little bit because that's a really fun and interesting way that we use data science for, what's a cybersecurity problem. It's also a larger, privacy, legal type of problem. But so Matt, can you just tell us a little bit about what deepfakes are?
Yeah, sure. I'd be happy to. So generative AI has the potential to be tremendously disruptive. We are already feeling some of those effects. Generative AI meaning ChatGPT, generation of artificial speech signals, generation of artificial faces and videos. So before getting to the question of what is a deepfake and how can we detect them, I just want to step back and answer the question of how can we teach a computer in the first place to determine that an image or a video contains a face. Sure. It's easy for us to take for granted how difficult this task is. Humans are highly skilled at detecting and identifying faces. We have a dedicated portion of the brain, the fusiform face area, that's specialized in face processing. Yet the face that we see in a picture is, in fact, a set of numbers in an array. So how can we get a computer to take that array of numbers and determine that it represents a face? So there's a couple of approaches that we can take. The first is to provide handcrafted features. And so you can look at pixels and detect boundaries in pixel intensity. And in this way, you can derive simple features like vertical lines, horizontal lines, and diagonal lines. You can then aggregate across those to derive more complex features like eyes, nose, and a mouth. And in this way, you can have a computer determine that a picture or a video contains a face. The other approach is to use deep learning. And so here we present the computer with a large number of pictures, some of which contain faces and some of which don't, as well as labels about whether or not the image contains a face. And then using deep learning, the computer learns a set of features to make those determinations. They may be the same features that we've provided in the handcrafted program, or they may be different features. So using either of these techniques, it's possible to feed a computer images and videos and get back information both about whether it contains a face and in some cases whose face it is. So to return to your question, what is a deepfake? Deepfakes are images and videos of people that have been manipulated using deep learning. I think it's important to note that since the onset of photography, people have found ways to manipulate images. This became much more possible with digital editing tools. And so up until a few years ago, the greatest threat was what's sometimes called shallow fakes. So these are pictures and videos that have been manipulated using digital editing software. And even though they're called shallow fakes, they can be highly compelling, and we still see them in multimedia today.
Yeah, and before you get deeper into that, you raise a great point I want to reemphasize for the audience. And so the term deepfake was just coined, I believe, in 2017 or so by a Reddit user. And it's specifically talking about using deep learning to create fakes. I think as the team that term has come more in the common lexicon, some people just use it broadly to mean a faked image or a faked video. And as you mentioned, there's been techniques using Photoshop and all kinds of products for years to fake something. And so deepfake can be used generally to mean faked, but technically, when we say deepfake, we're using something that was faked with deep learning.
Yeah, exactly. That's the key distinction here. And so deep neural networks, these are highly expressive machine learning techniques. And a face is among the most complex type of stimulus that we could produce. And so deep learning techniques are exceptionally well suited for producing such complex stimuli. And so like Tom said, a deep fake is specifically a face that's been manipulated using deep learning techniques. As compared to shallow fakes, deep fakes are more complex. So rather than just editing details of someone's face, it's possible to create altogether new faces that never existed. Deep fakes are harder to detect using traditional forensics techniques, and it's increasingly becoming the case that deep fakes are less manually intensive to produce. So all of these attributes of deep fakes are beginning to change the threat landscape. I just wanted to finish my response to your question by providing some recent examples of how deepfakes have been weaponized. And so two that come to mind, first is creating artificial social media profiles in order to amplify dissenting views. And then the second is targeting specific political leaders. So the recent example of this was the video of President Zelensky urging Ukrainian troops to surrender. So those are just two examples of how deepfakes are being weaponized.
Great, thanks. And so, with the use of deep learning, these fakes are much more sophisticated than some of the fakes that are used with photo video editing software. So that makes them much harder to detect because of their higher quality. So how can we go about detecting a deep fake?
Yeah, I think in order to answer the question of how to detect deepfakes, it's first important to understand the ways in which deepfakes can be created and generated. Jeff, do you want to talk about some of the ways that neural networks can be used to create deepfakes?
Yeah, absolutely, Matt. So when it comes to deepfake creation, you first want to gather as much data as possible. Neural networks rely on hundreds of thousands of data points. So maybe you need a couple hours of 4K video, right? And we'll stick with video to make life easier, because when you have video, you can break it into frames, as you said, Matt. And from those frames, typically using a deep neural network, you can extract faces and facial features, right? So from a video data set, you can now create an image data set. So just keep in mind, you have an image data set on hand, right? One type of framework that you can use is called a generative adversarial network, or a GAN for short. So a GAN is made up of two distinct neural network components. The first is the generator, which attempts to generate as realistic data as possible to generate fake data that is as realistic or similar to your real data, right? So at first, the generator network takes in random noise, and it'll spit out an image. That will be passed to the other network, which is called a discriminator network. And the discriminator network will take these generated images along with your dataset's real images, and it'll attempt to distinguish the real from the fake images, or the fake or the generated images. So it picks up on the ways that the generator generated these fake images, and it feeds that information back to the generator to help improve it. So now the generator is going to be able to make more realistic, it'll be able to make data that looks more similar to the real data. And they compete like this, iteratively, cyclically, until the generator is able to fool the discriminator on a certain percent of the images. So the generator's overall goal is to fool the discriminator into classifying fake images as real. So that's the first type of architecture. And Matt, you had mentioned autoencoders earlier. And as you mentioned, an autoencoder is a neural network architecture, and it relies on data compression. So we want to go from a higher dimensional space to this lower dimensional latent space. and get a more efficient representation of the raw images that we're putting in. So like Matt said, an autoencoder is composed of two components, the encoder and the decoder. So you feed in your raw images to the encoder, and that will map images to numerical code that represents the image. And this numerical code we can call latent vectors, so these lower dimensional base vectors. And the decoder will take that information and reconstruct an image, ideally that looks like the input image. One problem with the base autoencoder, though, is that when you have small perturbations in the images you feed in, or small variations in the input images, that can have a huge impact on the images that are extracted. So there's a type of autoencoder called a variational autoencoder, and it's very similar premises to the autoencoder. The main, so still compressing data, we still have an encoder and a decoder system. But the main thing that's different is the encoder output for the variational autoencoder now says we're going to constrain these latent vectors. They're going to follow a certain probability distribution such that each vector has a mean and the average, or the variance, which is the spread of the data essentially. So if you have 10 latent vectors that are sort of representing the raw image now, you'll have 10 sets of means and variances that are produced by the variational autoencoder's encoder. The decoder works the same, but by using that constraint, now any small perturbations in input images for the variational autoencoder has little impact on the image that's extracted from that. So those are two frameworks, but so a specific example of creating a deepfake would be something like, so let's assume I have two sets of faces. We'll say set 1 is Tom Cruise and set 2 is Brad Pitt. So we still have that encoder decoder system. So we have the two sets of faces, Brad Pitt and Tom Cruise. We feed both of those sets of faces into an encoder, the same encoder, but we have an individual decoder for each set of faces. So there's a decoder for the Tom Cruise faces and a decoder for the Brad Pitt faces, which individually generate images that should look like the original images. So you've trained this encoder-decoder system. Now what you can do is you can take the set of Tom Cruise faces, you'll pass it through that same encoder, but this time you'll pass it through Brad Pitt's decoder instead of Tom Cruise's decoder. And what that'll do is it will it'll keep the background of the Brad Pitt image, but it'll do a face swap where Tom Cruise's face is put onto Brad Pitt's face. So essentially at the end you'll have this set of images that have been altered or face swapped where all of the Brad Pitt images now have Tom Cruise's face on them. And again, because you have images, if you want to produce a video, you'll have to use some sort of outside software to stitch it back together. And so that's how deepfake creation and generation works. Matt, would you want to talk about deepfake detection methods?
Yeah, sure. And just to make the connection back to the broader discussion, what does the generation and detection of deepfakes have to do with cybersecurity? Well, it turns out that this is a real cybersecurity threat. On the one hand, the faces and voices of people contain important sources of biometric information, and that information can be used for authentication. So an adversary who can generate highly realistic faces and voices can defeat those forms of authentication. And then the second concern has to do with social engineering. It's one thing to receive spam email and to receive robocalls, but just imagine a skilled adversary who can also include a video capability and a voice capability in order to craft a highly compelling social engineering attack. So these are some of the reasons why it's important from a cybersecurity perspective to develop a capability to detect that a face is not authentic or has been manipulated in some ways. So when we as humans look at faces, we see things like a person's appearance and maybe their emotions. But a face is a complex stimulus that contains multiple layers of information. And each of those layers of information provides features that can be used to detect that the image has been manipulated in some way. So to give some examples of approaches to detecting that an image is a deep fake, one class of approaches look at microexpressions, so the movements of people's mouths, eyes, tiny muscles in the cheeks. A really clear example of this is looking at people's eyes in videos in order to determine that the blink rate is consistent with a real person. Another class of detectors focus on physiological measures. So it's possible to look at very slight changes in the luminance of pixel values on people's cheeks and foreheads, and from that to extract information about heart rate and respiration. And so using those types of signals, it's possible to determine that the heart rate and respiration in a video is not consistent with a live actor. Another class of approaches look at audio data, and for example, determining whether audio data is synchronized to people's articulation and whether the emotional tone in the audio data matches the emotions that are visible in the video. A final set of approaches, deep learning approaches, look for spatial artifacts. So within a given frame in a video, artifacts in pixel values across the face, or temporal artifacts, so looking across frames for slight variations in pixels that denote an artifact caused by the deepfake generator. So in reality, none of these methods is entirely effective against all different modes of generating deepfakes. And so the most effective defense against deepfakes is a layered defense that puts together a range of detectors.
Okay, great. Thanks, Matt. And so shifting gears a little bit, I got a question from the audience. I'll probably take the first stab of it, but you all can chime in. So the question is, how can you use data science to characterize compliance with controls out of, say, the US NIST risk management framework? So the NIST risk management framework, or RMF, specifies a series of security controls that can be used to assess the cyber risk of a system. It's used across the federal government. The short of the process is somebody will go through and determine which of the whole set of security controls is applicable for the system under study. Then you'll go through an exercise for each of the controls and determine how you adhere to the control. And then, the end game is you get your ATO, your authority to operate, that says that the cyber risks of the system are within acceptable range to field the system. And so one project I've been working on in this space is when we're using security testing tools, particularly code analysis tools and tools like this, they output a lot of data. And so I've been working on a project where we're taking the output of security scanning tools and doing a text similarity score to the NIST cybersecurity framework. So the tools typically put out more data than analysts can process. And so they have a triage and prioritization problem to say, which security alerts do I need to process? And so one answer is the ones that affect your ATO or your adherence to NIST security controls. And so we're looking at using these text similarity scores to say these outputs from these tools are similar to these NIST RMF controls. And so you should work on them first so you stay in compliance with ATO. But just in general, whether it's NIST RMF or just you have some type of series of security controls you want to make sure your system adheres to these properties. Any just off the cuff thoughts from either of you?
I mean, when you said document and text-based similarity things, that's what my mind went to, or just the overall realm of natural language processing. There's a large number of tools that can be used, whether it's just some basic, some off-the-shelf text similarity scoring algorithm. There's Google has BERT. There's a ton of pre-trained transformers that you could go to, and even when it comes to coding, there's a ton of natural language processing based pipelines that help speed up whatever you're trying to do. But like you said, my mind went straight to the natural language processing things like BERT and whatnot.
Okay.
And I'll add an example as well. So from the domain of Netflow Analysis, an organization can put sensors on its network. Typically, these are used to detect outflow of packets and inflow of packets. And so this is a way to monitor compliance with certain types of regulations. For example, you can detect that certain users in the network are bypassing secure VPN. That may or may not be malicious, but it is something that you could flag as a security risk.
Mm-hmm.
It's also possible to use flow data to detect signs of data exfiltration. So in that case, detecting what truly is a malicious behavior. But again, the issue is that the volume of packets being transmitted is so great that it's not possible to manually track them. It's also probably not possible to handcraft a set of features to say that something that's occurring is malicious or risky. So here it would be beneficial to use machine learning in order to train a computer to make those determinations.
Okay, very good. Yeah, in the tech similarity work I was mentioning, so that's looking at sort of the whole set of controls and determining which ones. If you went control by control, then there's probably some other techniques you could use to say, am I in compliance with this control, or have I detected some type of violation of the control policy? So then it would become sort of a control by control, context dependent thing. But putting that aside, any other just general areas that you think we can use data science for cybersecurity besides the ones we've talked about so far?
I'm going to beat a dead horse and stick with email analysis. So businesses generate a great deal of email traffic every day, large volume of email traffic. And occasionally emails that you think are trustworthy turn out to be malicious. Maybe it's spam per se. But like I mentioned earlier, you can use data science methods to create a spam filter to classify emails as either benign or malicious. And you can use information about, the body of the emails themselves, as I mentioned before, sentiment scores, maybe very simple words are misspelled. Maybe this person sends 10 emails in a 5-second period. But one of the reasons that I think it's so important is the concept of an insider threat, right? So an employee has this ability to access an organization's servers, or just has general information about them, and they click one wrong link, and now this adversary has just gained access to this organization and can do some devastating things and harm the organization.
Yeah, so to return to the topic of Netflow analysis, organizations generate a tremendous volume of Netflow data, and they can place sensors in their networks in order to track aspects of those data flow. We've been talking about the detection of threats, but instrumenting one's network and applying data science methods can be used for more than just that. It can be used to measure the performance of the network and to predict how the network will respond to different external and internal perturbations. So in this case, just predicting the performance of the network in the course of normal events. Additionally, ML can be used to create detectors to determine that different traffic flows are indicative of a threat. I think there's two key questions in this regard that are of interest in our active areas of research. The first is minimizing the number of false positives. If you look at the volume of emails that an organization receives, the volume of net flow data that takes place, even if you create a detector that has a very low false positive rate, when we're talking about hundreds of thousands of events being classified, even a low false positive rate may result in an unacceptably high number of false positives. So one question in this regard is, how can we minimize the false positive rate, or take those events that the computer is classifying as being potentially problematic and then further group them in a way to make it so that a human analyst can go through those effectively. The second thing, and we haven't talked about this so far during this webinar, Typically, we don't see machine learning as replacing human decision makers. Rather, it will be a component of a human-machine team. And so what are the implications for selecting algorithms that are inherently interpretable to a human decision maker, or complementing our methods with different explanation interfaces? These are just two approaches adopting inherently interpretable algorithms and including explanation capabilities to allow human decision makers to understand how the machine arrived at the determination that it did.
Great, thanks. Take another audience question. I'm probably going to break this into a couple parts, but the question is pretty straightforward. It's, how do you think you could go about using a GAN to detect novel zero-day exploits? And so zero-day exploits, for those that don't know, are novel attacks that haven't been seen before. So it's a new piece of malware there's no signature for. It's something you don't have defenses and mitigations for, and so it's hard to detect. GANs are a type of adversarial network. I don't know if Jeff, just that's why I'm breaking it apart. Can you give the audience just a quick couple-minute explanation of a GAN and how it works, and then we can talk about how to apply it to a zero-day?
Yeah, sure. So again, as I mentioned before, a GAN has two components with some real data set aside. We have the generator network and the discriminator network. The generator network takes random noise as its input and extracts whatever type of data that you are worried about, whether it be images or videos or speech patterns. And it feeds that back to the discriminator network, which now takes the real data in as well, and it attempts to distinguish between the real and the fake data, the generated fake data and the real data. It picks up on some of the ways that the generator network generated its data, and it passes that information back to the generator. So the generator now has information about the data itself and the way that the discriminator classified the data. So it's now going to generate more realistic data. And they play this game until the generator network essentially fools the discriminator enough into classifying the fake data as real.
Great, thanks, Jeff. And so to this specific question, we have these, and again, we have two competing models, and I could see one model generating what it thinks are zero-day exploits or novel pieces of malware, and another one trying to detect them. And that way we could train a detector to detect 0 days. But Matt, any ideas on how you might set up an experiment or a research approach?
Yeah, so typically the adversaries approach here, so they would train the GANs and then they would retain the generator and discard the discriminator. That's right. Yeah, so one potential approach as defenders would be to train a large number of GANs, and we would take, the opposite. We would discard the generators and retain the discriminators. And I say retain the discriminators. I think that the idea here would be to follow an ensemble approach, train a large number of models. Each model, the discriminator from each model, will arrive at a slightly different solution for detecting zero-day exploits. And then the ensemble prediction will be more accurate than the prediction of any one discriminator that was retained.
Yeah, I think it's a great question because it sort of reinforces the need for data science in the space. So folks have been combating malware for a long time, and it's a cat and mouse game, right? So the adversaries create malware, we create hashes and signatures, and we learn how to detect that malware, and they learn how to evade those detections. But now with machine learning, they can do it at scale, right? And so we need to defend at scale, and that's where data science and machine learning can really help. Next question from the audience: are there cybersecurity challenges different for intranet apps behind firewalls versus public domains? And so that's a cyber question, but to put it into a data science question, from my perspective, it's kind of a feature engineering question, right? And so when we're doing data science and we're doing feature engineering, the more we know about the domain and context, the more we know which features to focus on and to label and to use in our models. And so in a case like this, if we knew we were doing an intranet app that we were defending versus something that was public deployed, then we know that, the origination of the traffic, where it came from, those type of things might be features to focus on. So do you just want to talk a little bit, you could talk about this problem or just sort of feature engineering in general and how that's part of data science?
Do you want to go? Sure, yeah. So I guess the main thing that comes to mind, because you did a decent job, Tom, being comprehensive with it. A lot of the time when you have a data science problem in general, you typically have a lot of features that describe the overall data, and a lot of the features are not necessary. So the worst case is where you have more features than, data points themselves. But also, maybe you have, a problem where only 5 or 6 of the 25 to 30 features you have are relevant. What you can do, it's more common in something like a regression model, but overall you can look at things like feature importances. So you can train a model, whether it be a classifier or a regression algorithm. You can train a model to predict whatever it may be, and then afterwards you can look at things like, if it's a regression problem, you can look at the weights or the coefficients and see which weights are biggest in absolute value. These are the features that are most impacting the data, and so we would call them the most important features. So that's what comes to my mind first, is just looking at feature importances once you train a model, and then once you figure out maybe the 5 to 6 most important features, you can retrain the model, and having dropped out the features that weren't important, you train this new model and then do a comparison of how well it did versus the initial model.
Great, thanks. So we just have a few minutes left here. Just I'll ask some parting comments from Jeff and Matt. You obviously been working in data science for a long time, but if someone's new to data science and they want to apply it to their cybersecurity problems, just why don't you give me maybe a quick step? How would you tell someone to get started in this space?
Yes, I would immediately say, ask for help. Reach out to expert data scientists or machine learning engineers, whatever it may be, and just pick their brain. And it can be in-house in your organization or outside of your organization. There are a lot of experts here at the SEI focused on those things.
Great, thanks.
Yeah, and I would add to that one could develop their skills independently. There are tremendous resources available online, written tutorials, interactive tutorials, books, libraries that one can download. So there are tremendous resources to get started. However, in addition to that is formal instruction in a particular domain. For example, to see how to take general purpose ML algorithms and apply them in the context of cybersecurity. And that's both to make sure that you understand kind of the ins and outs and nuances of applying ML in that particular domain, and also understanding kind of the problem set and the range of applications of ML that have already been pursued.
Very good. And so I mentioned in the introduction that we do have a new CERT, Applied Data Science for Cybersecurity Professional Certificate Program. So that's one way, folks, if you want to learn these skills and how you can learn some data science skills, in particular learn within the cyber domain. This is a self-paced e-learning platform, so please check that out. But there's lots of other ways, as you just mentioned, that folks can get into it. And so there's a need to apply data science cybersecurity. So we want to see folks get involved doing that, whether it's through our training program or any self-learning or any other ways they can do it. I think the biggest thing is just to get started. You can play around. There's a lot of models and information on the internet, open source code, pre-trained models, so you can get up and running. I did want to go back. I mentioned one thing too. We talked a lot about deepfakes in this session. We have some good information on the SEI website about deepfakes you can check out. Particularly, we have a blog that talks about how deepfakes are created. A lot of good information in there, particularly some talk about the post-processing that goes into creating the deepfake. So the models don't spit out perfect deepfakes. There's a lot of post-processing editing work to make the really good deepfakes. A lot of information on that in there. All right, so I'd like to thank everyone for joining us today. I'm sorry we didn't get to all the questions. We answered as many as we could. I'll maybe try to reply to some in the chat after the session. This session will be archived on the SCI YouTube channel and on the SCI website, so you can pull it up and watch it again in the future. I'd like to thank everyone for joining us today.